All right, Physics 3030, the universe. This is lecture 4. We'll finish up talking about astronomy today, do a little review, and then start talking about the Hubble expansion. And so we'll go through Doppler effect and redshift review. If you haven't already, okay, so before watching this video, you should really go back and watch the supplemental videos on the Doppler effect and on redshift, okay? Because I'm going to really just jump into it here. Those videos should cover most of what you need to know about these things. And then we'll talk about Hubble expansion, cosmic redshift, Hubble's law, and if we get to it today, we'll talk about the Big Bang. So we're really going to jump into this cosmology stuff today. Okay, so let's get rid of this and move on to the next slide here. So the first part of the review that I want to talk about is just remembering now, after you've watched these videos about the Doppler shift and redshift, that what directions we go on the magnetic spectrum. Now remember, we're talking about, when we talk about shift lines in astronomy, what we're really doing is, remember that at some point we're going to be taking some spectra, right? And those spectra look something like this. You have some picture, and you have lines in different places. And the sort of pattern of those lines, the way how far apart they are and things like that, they don't really change. And the pattern is, we expect the patterns depending on what the star is made out of or what type of explosion it is or things like that. And we assign to each of these points we know some jump of the electron, actually, that is what it is. And we'll talk about this actually in the next lecture, but we know exactly what's going on here. So I can tell you that this line comes from an excited hydrogen atom, say, or something like that. It's the shift of those lines, and they all shift together. It's the shift of those lines that we're looking at when we talk about redshift and blue shift. And I just wanted to review a couple of things. When something is coming towards us, so if something is coming towards us, it's almost like we add to the energy of it as it comes to us. Remember those talks about the redshift. And if the energy goes up, we actually go towards the blue side of the spectrum. So the blue side of the spectrum here, energy goes up. Okay, even though the wavelength is going down, the frequency here, the frequency is going up, and that's really the telltale sign about the energy. Think about it this way: if your little brother or sister was running around the room and moving really, really fast, you'd say they had a lot of energy. Well, that's what these little bumps are. There's lots and lots of little bumps in here moving along. So high frequency equals high energy. And if something is moving away from us, it's sort of like it takes energy for it to catch us, so its energy goes down, and then in that case, it's redshifted, and that's where the energy is going down. Okay, and the wavelength is getting longer, and the frequency here is much, much bigger. So it's just a little review of what we should remember about how the way the redshift works. And there's a formula for this, and it's important for you to know the formula. And the formula looks something like this. The velocity of something, okay, we can tell the velocity of it. We call this the radial velocity. And I'll talk about that in a second once I'm done with the equation here. But the radial velocity over the speed of light, so this is of course for light. This equation would be different if it was sound. But the the radial velocity of something over the speed of light equals the change in the wavelength. Remember, this symbol is called lambda, but that's just the wavelength. The change in the wavelength over the wavelength that I would measure in the lab. Okay, so this is what I would know. It's really talking about this reaction up here with the hydrogen. That's that is the thing I know if I measured it in the lab. Now the laws of physics say that the laws of physics should be the same everywhere, right? And so because we know what it is in the lab, we should know what it is out in space at the star. And so this tells us this is the wavelength that we know that it should be, and this change in the wavelength then tells us how fast it's moving. Now I can rewrite this delta here might be a little confusing to some of you. Delta is just the change in the wavelength, and here what we mean is the change in the wavelength is sort of the observed wavelength minus the lab wavelength. Okay, so that's just the difference between what we see and what we know it should be, right? And we're going to divide that by the lab wavelength, and that still equals the radial velocity over c. Okay. Now, this radial velocity thing is because we're sitting here on Earth, and we see a star somewhere out here, say. Okay, let's make that red since it's shining at us. Okay, and the star could be moving. It doesn't have to be moving exactly towards us or away from us, right? It could be moving at some angle like this. And all we can really tell is the amount of velocity, how fast it's going in this direction. And that direction is the rate, what we call the radial velocity, because it's along this radius, right? If this is a big circle around us. And so it's just this part of the velocity that we can see. So the radial velocity is always less than or equal to the total velocity, right? So the radial velocity could be all of it. So it could be just coming towards us, or it could be going a little bit sideways, and we can't see that because this redshift only tells us, how far away from us it's moving. Okay, so that's just a quick review of what the things I want you to know about redshift, and this is all sort of linked to the Doppler effect. So again, you should have watched those videos before this, and this will make a lot more sense. And okay, let's clear this screen and move to this blank page here. And I want to sort of sum up some of the things that we've learned over the last few lectures in the form of what it is that we can measure about the universe. And there are other things we can measure, and I'll introduce those as we go along, but these are some of the important ones. Okay, and so we've talked a lot about distances, right? And in that we have, when we talk about distances, we use a special unit, right? So we talked a little bit about light years, and we talked about light years because that's the most useful unit for talking about distances, one of the most useful units for talking about distances, of course. And I would say that over here, light in general is our biggest tool, our best tool, because it's really the only thing we get. I mean, there are other things that we'll begin to see, and we'll talk a little bit about those, and there's things that we want to be able to see, like gravitational waves and things like that. But light is all we've really got from out there, okay? And so we're going to use it a lot of the time to measure things. But back to distance, okay? So this is our units of distance. We also have another units called the parsec, and that's from one of our ways of measuring distance. This is called parallax. And remember, parallax is just our change in position making a star look like it's moving along the background. And the equation for this, right, is that the distance in parsecs, that's the abbreviation for parsecs, is equal to 1 over the angle that it changes, where the angle is in arc seconds. Okay, so that's our first tool that we learned how to use. Another tool that we learned how to use was something called the inverse square law, right? And remember, the inverse square law says that the flux that we get here on Earth is equal to the luminosity over 4 pi times the distance squared, or r squared, the radius away from us, if you'd like. Okay, and this leads us to another formula for the distance, okay, which is that d is equal to, it's going to be the square root of this stuff, L over 4 pi times the flux, All I've done here is solve that this formula up here. Okay, so we can use the inverse square law to measure how far things away are. And remember that the tools of the trade here are those Cepheid variable stars, right? Cepheid variables. And there's a couple great videos about Cepheid variables if you want to learn more about those. And supernovae. And particularly here, type 1a. Remember, these are special stars. And the thing that's special about them is that we know L. Okay, so we know their intrinsic luminosity. And that's the big deal about these stars. That's what helps us to calculate the distance. And we need to know L, right, to be able to put it up into this equation up here. Okay, and then the last thing, again, back to light. So let's go sort of this column over here. So light's our best tool, right? And we can use it, remember, just to do those, to look at those spectra, so we can measure spectra. And so the spectra are going to be twofold. One important thing that I haven't really talked about very much is that, again, it tells you the composition of things. It is actually these spectra that allowed us to know that the sun was made of hydrogen and helium. That the sun, so the sun is mostly hydrogen and helium. And it's because of these spectra, because we saw those lines, and again, those lines are really specific. And they tell us everything we need to know. And then the other thing we can do is not just composition, but we also know velocity. So we know how, at least a little bit, about how things are moving. And again, this is the radial velocity, so it's how far away from us or towards us it's moving. And this is, of course, using the redshift. And, of course, things could be blue shift. And we talk mostly about redshift because of the Hubble expansion, which we'll talk about a little bit later. And, again, that equation, which we just wrote on the previous page, is the radial velocity over the speed of light is the change in the wavelength over the wavelength in the lab. Okay? These are pretty easy formulas, and we're going to use these. You'll see this stuff come up over and over again. Okay? And so that's our toolbox of what we have. So let's now start talking about what we can use these tools to figure out. Okay? So what we want to talk about is one of the amazing observations that this gentleman here made, and his name is V.M. Slipher. Okay? And in the early 1900s, so right around 1914, we know that actually Edwin Hubble heard about this in 1914 directly from Slipher. Slipher was making measurements of redshifts of galaxies. So he was measuring the redshift of galaxies. Now I want to make a point here, maybe up here in the margins. We see blue shifts and redshifts. Okay, and we see both of these things, but it turns out that if something's really far away, we mostly only see redshift. But in the local group, and even actually the closest galaxy, is blue shifted to us. Okay, so we see blue shifts. We see blue shifts of galaxies, and when galaxies are spinning, and this will come up later, but when galaxies are spinning, right, galaxy, and it's spinning, well, one end of it might be coming towards us, and the other end of it might be going away from us. So we see a blue shift on one side and a red shift on the other. So we do see blue shifts, but we're going to talk a lot about red shifts. And again, most of the things that are really far away from us, we see red shifts. So V.M. Slipher, he measures these red shifts of galaxies. And unfortunately, no one really believes him. Even though he's making good measurements. So he's not really believed because these measurements corresponded to something like 600 miles per second. Per second, right? So that's pretty fast. Something is moving 600 miles per second. And no one knew of anything that could move that fast. So a lot of these measurements he took were kind of poo-pooed or whatever. No, nothing. It must be something else. There must be some other effect because 600 miles per second is really, really fast. Okay, so that's sort of the where we're standing in 1914. All right, so let's get rid of this layer, and we're going to move on to the next slide, which still has Slipher on it. So I'll still write his name up here. That's Slipher. This guy down here, this is Edwin Hubble. He's the next character in our play here. Oh, Edwin Hubble. And Hubble is very famous. Many of you may have heard of the Hubble Space Telescope that's named after him. And this picture is a pretty famous picture. This is the Hooker 100-inch telescope, and this is at Mount Wilson, and this is where Hubble made his discovery, which I'm going to talk about in a second. This is the largest telescope in the world. So in 1929, Hubble was looking at Cepheid stars. Remember those Cepheid stars? Cepheid stars have an interesting cycle where the brightness oscillation actually tells you about the intrinsic luminosity, right? The intrinsic brightness. Now, luminosity and brightness are just synonyms for each other, but how the star's brightness oscillates tells us about the intrinsic luminosity of the star. And this is the observation that Henrietta Leavitt made earlier in the century, working from the Harvard Observatory. And when he was observing these stars, he realized that the further a star was away, so as distance increased, it turned out that the recessional velocity, so that radial velocity, right, that velocity also increased. Okay, and so the graph of this, a graph of something like this, would look like this. Okay, so we have velocity here going up, and over here we have distance. And you have if you look at the Hubble plot, it looks something like this. And there's more stars closer by, right? Because of course we can see more of these Cepheid stars closer to us than we can further away. It's harder to resolve them further away. And the line that you can draw through this looks something like this. Okay, and so this thing has some slope. And we're going to call that slope actually h sub naught, which is named after Hubble and is called the Hubble constant. We'll talk a little bit about this later. So we'll definitely bring this up a little bit later when we're talking about the age of the universe. Okay, so he gets a graph that looks like this. Oh, the further something is away, the faster it's moving. Now, the amazing conclusion that you can make from this is that the universe is expanding. Okay, and we're going to spend some time now talking about why this means the universe is expanding. So the universe is expanding. Now, I have to say that this is probably some knowledge that you grew up with, right? But this is not something that was known at the time. In fact, Einstein famously screwed up some equations because he thought we were in a steady state. So he thought steady state. Let me put some more words. We were in a steady state. So Einstein, who was a pretty smart guy, thought that the universe was static. It wasn't moving, right? Static, in this case, means was moving. And so he thought we were in a steady state, and he screwed up some equations because of this. And and he did those equations in like the 1915, 1916. And so no one really thought at the time that the universe was actually moving, that it was expanding, that it was actually changing. There's two things important here. One is that it's expanding, but also just the fact that it's changing at all was a huge, huge discovery at the time, and that made Hubble very, very famous. And all kinds of good things happen from that. So this is really one of the first big observations that we make about the cosmos that totally changed the way we thought about what was going on. Now, Einstein had some equations that people were working on, a number of folks were working on, and so this ruled out some cosmologies. Now, we'll talk a little bit about general relativity in a couple of weeks, maybe more than a couple of weeks, but the equations of relativity have solutions where the universe is expanding, but they just got thrown out for a long time until this discovery by Hubble. Okay, so let's clear this ink layer, and then we're going to move on to a clear slide here, and we're going to talk a little bit about how we know this relationship means that the universe is expanding. Okay, and what I'm going to do is I'm going to show you what happens if the universe is expanding, and that will show you that the velocity increases as the distance increases. Okay, so what I'm going to do is I'm going to draw a balloon. Okay, so this is kind of a half-inflated balloon, and on this balloon I'm going to put some ladybugs. Okay, and I'm going to put them in a pretty uniform grid here. Okay, so here are our ladybugs. That's a good amount of them. Let's give them some black dots since they're ladybugs. Now, if we're in a universe that expands, and of course we all know that we can expand a balloon, right? So what we want to do is, this is at some time, lowercase time. Okay, so t equals 0 seconds, say. Okay, and now I want to blow the balloon up. So I'm going to blow the balloon up, and I'm going to make it really big here so we can have some fun with this. Okay, when I blow up the balloon, the position of the ladybugs isn't good with respect to each other, isn't going to change. Look at that, I even made it as lopsided as I did the first one. So the position of the ladybugs isn't going to change, and their size isn't going to change either. But they are going to spread apart from each other, right? So as the balloon expands, the ladybugs spread apart from each other. Here we go. Okay. So, of course, their distance between each other has increased. Now, we need to look at a couple of different things here, right? So I'm going to say that's at t equals 0 seconds. Let's say this is at t equals 1 second. Okay. So again, remember that delta symbol. So we're going to say that the change in time equals 1 second, right? So that's equal to the final time, which is 1 second, minus the initial time, which is 0 seconds. So 1 minus 0 is 1. Everybody better be able to do that kind of math, right? So that's the change in time. Now, the distance that these guys have the velocity of these guys, if I want to measure the velocity of them, right? The velocity equals the change in distance, the change in the distance over the change in time, right? And if I look at the distance between, say, these two guys, right, I get one distance, and let's call that, we'll call that D. We'll just call that, what do we call that? Let's just call that 1 meter. Let's call that 1 meter, Okay, so that distance is 1 meter, and that's 1 second. So between these two, from here to here, we get a velocity that is 1 meter per second. Okay, so that's pretty easy. So they've sort of moved apart further. 1 meter. Okay, so what? Maybe I screwed that up a little bit. Okay, what I mean to say is that this isn't. Let's erase this. Whatever this distance was, okay, its changed in distance is equal to 1 meter. So the whole distance isn't 1 meter, but it changed. It got bigger by 1 meter. Whatever it was, it got bigger by 1 meter. Okay, so that's what I mean. Remember, this is a change. This is a change in distance. Okay, so it's changed in distance by 1 meter. But if that change, if it's between those two ladybugs has changed in distance by 1 meter, then the change in distance between these guys, so the change in distance between those guys, between those two, is equal to 2 meters, because they're double the distance away from each other, right? Because if this is increased by 1 meter, then this is increased by 1 meter. That means the distance between the two of them has increased by 2 meters. And so so if that's velocity 1, then the velocity between the two further ladybugs is equal to 2 meters per second. Okay. Now, why are these different numbers? Because the ladybugs are further apart from each other. Okay. So this is the idea of the Hubble expansion. These two ladybugs, they're close to each other, they're receding from each other, they're moving away from each other, but not as fast as these two ladybugs that are further apart from each other. Okay. Now there are supplemental videos about the Hubble expansion, and this is just to kind of give you a little bit of a primer on it, but you should take a look and see and watch those videos to get a little bit better understanding of this stuff. Okay. The main point, though, let's erase some things. I'm going to just do this by hand instead of erasing all of it. But some of the things that I want to sort of highlight about this is that, remember that graph that we had earlier where I had the velocity here, the distance here, and I said, okay, there's a straight line, and we call the slope of that line h naught. Well, this gives us the equation, right? That the velocity of something depends on the distance, right? So as the distance goes up, remember this is a direct relationship, right? So as the distance goes up, the velocity goes up, okay? And there's a constant in here called the Hubble constant, okay? Again, so that's the Hubble constant, named after the man who found it, figured it out. Okay, and just to give you some idea, so this law, this is called the Hubble Law, which just says that the further something is away, the faster it's going. Okay, and we can measure what the Hubble constant is, and there's lots of different ways to measure it, and what we basically do is take the average of all of those, and the current value of h is 73 kilometers per second per megaparsec. Okay, so get this, right? This first part here, try and understand this. This first part is a speed, right? So this is saying that I increase 73 kilometers per second for every megaparsec further I go. Now, remember, megaparsec is million parsecs, and a parsec is about 3 1/4 light years. So this is like every 3 million light years away, I'm going this much faster. So this seems like a lot faster. This seems like a pretty fast number, 73 kilometers per second. But I have to go 3 million light years away to get that much faster. Okay, so that's pretty crazy. But that's the Hubble law, and that's the number that we can currently measure. And I want to point out something here as well, with the Hubble law. So I want to take our definition of velocity, right? So velocity is equal to some distance over some time, change in distance over change in time. So I can solve this for time. So I just kind of flip things around. So the time is equal to the distance over the velocity. But I have this special velocity, so let's put that into the equation. And then I get that the time is equal to the distance over the Hubble constant times d, where I've just taken the box in red and put it in as our definition of v, but the d's, they cancel. So I end up getting that some time is equal to 1 over the Hubble time, or 1 over the Hubble constant. Now, this is a pretty big number, and it talks about the expansion of the universe, okay? And what this means is this gives us some idea of the age of the universe. This gives us some number about the total age of the universe. And why is that? Why is that? Because think back to this balloon here, this little balloon, right? Go backwards in time. Start with the big balloon, go to the little balloon, and if I get smaller and if I keep going backwards in time, I'm going to get smaller and smaller, right? And if I keep going smaller and smaller, smaller and smaller, 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 I get to some tiny little dot, right? And that tiny little dot we can think of as the beginning. That's the beginning. All right? And if I play that in reverse, if I play that dot in reverse, it looks like a big explosion. And we call that, what do we call that? The Big Bang. The idea that the universe is expanding implies, so expansion implies the Big Bang. Because if we're expanding going into the future, in the past we came from some tiny little dot. And this rate of expansion, which is what the Hubble constant is, tells us something about the age of the universe. Okay? And if we look at the age of the universe, then, or if we look at this time and we calculate it, 1 over the Hubble time ends up being 14.4 billion years. Okay? And there's a lot of debate about how old the universe is, and this number is probably a little big. Why is it a little big? Because this implies that the Hubble constant is actually a constant, and though we can fit it to this line up here and have it be a constant, it might not have always been a constant. And in fact, we know today that it's not. This has a lot to do with what dark energy talks about. And so we know that this number is actually a little bit smaller, but this is a good first guess, and it's within a billion years. So a billion years, what's a billion years among friends, right? So crazy. Hubble's tiny little, not tiny, but his simple observation that the further away from something we go, the faster it's receding from us, leads to all kinds of implications about the universe. It implies that we're expanding, that the universe is changing, that at some point we started from some tiny little spot, and that when we play that back in reverse, we get the Big Bang, and we can even start to tell what the age of the universe is from this. Okay, this is crazy stuff, good stuff, amazing to be able to tell all of this from really one simple observation. At least that's what started it all, right? And so we're going to clear that for a second. And the last thing I want to talk about today, if I can get my pen back up here, is called cosmic redshift. And this is just sort of anticipating some of your questions maybe, and to talk a little bit about this. So the idea that these galaxies that are really far away are redshifted really has to do with the expansion of space-time. So space and time, but we like to just call it one word, space-time, the expansion of space-time. And it's the idea that as sort of the grid, let's see if I can maybe draw a little diagram of this, right? As the grid expands, so I go to a bigger grid here, as the grid of space-time expands, right, a wave that's sitting here in this space-time expands here, right? And because it expands, the wavelength gets bigger. So the change in wavelength is positive, it gets bigger, and that basically redshifts us. And so this cosmic redshift is due to the expansion of space and time, and we only see it on large scales. And that's why everything that's really far away from us looks redshifted. We only really see it when things are really far away on large scales. Because it takes a lot of expansion of space-time to be able to see it is one reason, but also because of gravity locally holds us together, right? So you could ask the question, this is really the answer to the question, why aren't we expanding? And the answer is that gravity, the gravity of us, the stuff that is with us and in us, it all attracts each other. And because it attracts each other, it's not expanding, right? That's why the sun and the earth, they don't move apart from each other. They don't move apart. I mean, they oscillate a little bit, but that distance, the average distance doesn't really change very much, at least not due to this expansion. Okay, it could change because of drag forces and all kinds of other things like this. But we're not expanding. Even within the galaxy, we're not expanding. Even within our local galaxy cluster, we don't really see much of this expansion. But on large scales, we see this expansion. So we're looking, so I should highlight this. Hubble is looking really far away to see this stuff. Okay. All right. So again, there are supplemental videos to talk about the Hubble expansion and cosmic redshift. You should take a look at those, and hopefully this is pretty clear stuff. We're going to have some homework and some writing about this. So, all right. Until next time. Thank you very much.